All right, let's dive right in. Have you ever just stopped and wondered, what makes you, you? What's happening inside your head that lets you think, feel, and even just lift your hand? Today, we're going deep into the incredible world of neurotransmission. It's the electrical and chemical dance that creates the spark for every single action you take.
You know, every single thing you do, from blinking to thinking about what to have for dinner, it all starts right here. It's a conversation happening between your brain cells. And it's not just any conversation. It's this amazing storm of chemical whispers and electrical shouts. So the big question is, how does this microscopic communication actually work? And maybe more importantly, what happens when those lines of communication break down? Let's get into it.
So, to really understand this whole conversation, we first have to meet the key players in the story. We've got to meet the brain's tiny, absolutely tireless messengers. And here it is, the absolute star of the show, the neuron. This is the fundamental unit of your nervous system. Think of the main part, the cell body, as its command center. Then you have these branchy-looking things called dendrites. Their whole job is to listen, to pull in signals from other neurons. And then you've got this long cable, that's the axon. And its job is to speak, to send that signal blasting out to the next cell in line. Okay, so if neurons are talking to each other, what language are they even speaking? Well, they're speaking in chemicals, and these chemicals have a name, neurotransmitters. They are, quite literally, the words that carry a message from one neuron to the next, flying across this teeny tiny gap called a synapse. And this is the perfect way to picture how it works. It's all about a lock and key system. The neurotransmitter, that's your key. It zooms across the synapse and fits perfectly into a specific spot on the next neuron. That's the lock. And when that key turns in the lock, boom, it opens up a channel, letting charged particles or ions flood into the next cell. And just like that, the message gets passed on. And there are so many different types of these chemical words. You've got dopamine, which is all about movement, motivation, that feeling of pleasure. Serotonin helps regulate your mood, sleep, even your appetite. Acetylcholine is absolutely critical for making your muscles contract. And norepinephrine, that influences things like alertness and decision-making. This, by the way, is exactly where stuff like your morning coffee or certain medications come into play. They work by tweaking the levels of these very messengers to change how your neurons are talking. So we have the chemical message, the whisper. But how does that turn into the electrical shout we mentioned at the start? Let's follow the signal as it transforms from a chemical into a full-blown electrical pulse. Right, so when those ion channels pop open, they create these little electrical signals. But here's the thing, not all signals are created equal. You've got whispers and you've got shouts. The whispers are called graded potentials. You can think of them like ripples in a pond. They're small, they're local, and they fade out pretty fast. But then you have the shouts. These are action potentials. This is the main event, a huge all-or-nothing electrical pulse. Once an action potential starts, it is an unstoppable wave that barrels down the entire length of the axon. This table really breaks it down nicely. But the big thing to notice is that action potentials are all or none. They either fire at full blast or they don't fire at all. There's no in between. And what's really crucial is that an action potential only happens if the neuron gets excited enough to hit a certain threshold. This is the brain's quality control, making sure that only the most important signals get the green light to travel long distances. Okay, so if a neuron has to hit this threshold to fire, how in the world does it decide when the time is right? Well, this brings us to what I like to call the neuron's grand decision. It's a process called neural integration. Get this, a single neuron can be listening to messages from thousands of other neurons, all at the same time. Some of these messages are excitatory. They're like a yes vote, telling the neuron, go, fire. Others are inhibitory. They're a no vote, saying, nope, stay quiet. The neuron's job is to act like a tiny election official, constantly tallying up all these yeses and nos to make a final decision. So here's exactly how that election goes down. First, all the inputs flood in, a whole mess of yes votes, causing little sparks of excitement, and no votes, trying to calm things down. Second, the neuron tallies them all up. It adds and subtracts all those little graded potentials. Finally, the decision is made. If the grand total of all the yes votes is strong enough to push the neuron's charge up to that critical threshold, bam, it fires an action potential. It shouts its message down the axon for the next neuron in line to hear, loud and clear. You know, this system is just so incredibly elegant and efficient when it's working, but it's also really, really delicate. So what happens when this intricate web of communications starts to break down? When that neural communication fails, one of the most obvious and visible results is a movement disorder. And it's just what it sounds like. These are conditions that cause all sorts of abnormal movements, things you want to do and things you don't. Let's look at a really well-known example. In Parkinson's disease, the breakdown is heartbreakingly specific. Remember our friend dopamine, the neurotransmitter involved in smooth movement? Well, in Parkinson's, the brain cells that make dopamine in this one critical area, the substantia nigra, they just start to die off. The chemical words for smooth, controlled movement are literally being erased. And this picture, wow, it makes the impact brutally clear. On the right, you see that dark, healthy tissue of a normal substantia nigra, just packed with dopamine neurons. And on the left, in the brain with Parkinson's, that area is faded, it's pale. You can literally see the communication system being wiped out. And the result of losing those messengers is a devastating set of symptoms. You've got the 4 cardinal signs: a tremor when at rest, a profound slowness of movement called bradykinesia, intense muscle rigidity or stiffness, and major problems with balance. All of it, stems from the loss of one tiny messenger in one specific neighborhood of the brain. Another catastrophic communication breakdown is a stroke. But here, the problem isn't a specific messenger chemical. It's the entire infrastructure. A stroke is the rapid death of brain tissue because its blood supply gets cut off, which silences those neural conversations, and often it's permanent. Now, the vast majority of strokes, something like 85 to 90% of them, are ischemic. You can think of this as a plumbing problem. A blood clot gets stuck in an artery in the brain and creates a blockage. It's like a clog in a pipe, and it starves all the neurons downstream of the oxygen they need to survive. The other type is a hemorrhagic stroke. So if an ischemic stroke is a clog in the pipe, this is a burst pipe. An artery actually ruptures and starts bleeding into the brain tissue. The pressure from all that blood then damages and kills the neurons around it. It's a completely different mechanism, but the result is just as devastating. But it's not all bad news. And this is the really exciting part. We're actually learning how to get in there and fix things. Technologies like deep brain stimulation, or DBS, are offering real hope for conditions like Parkinson's. Doctors can implant these tiny electrodes deep inside the brain and use them to send electrical pulses that directly correct the faulty signals. They're essentially learning to speak back to the brain in its own electrical language to help restore function. It's amazing. So, we've gone on this incredible journey, from the whisper of a single chemical messenger to the grand electoral decision of a neuron, and we've seen the tragic consequences when it all goes wrong. But these new technologies, like DBS, they bring up one final massive question. As we get better and better at decoding and maybe even rewriting the brain's fundamental electrical code, what are the limits? How much can we repair? And maybe the even bigger question, what might we one day choose to enhance?